All right, let's get right into it. Today, we're doing a rigorous technical status review of REBCO high-temperature superconducting, or HTS, integration. We are strictly focusing on the physical and electromagnetic constraints of modular saddle coils. We're going to dive deep into the mechanisms, the quantitative limits, and the exact failure modes to assess our transition from ambient copper testing to a fully superconducting matrix.
Now, I want to anchor our analysis on a fundamental reality. Moving into this HTS REBCO phase, it is definitely not a simple linear scale-up. It is a complete shift in material physics. We simply cannot assume that our baseline data from ambient copper coils will smoothly translate here. Blind guessing these limits will cause catastrophic failure because we are now dealing with incredibly brittle ceramics and extreme thermal sensitivities.
To methodically assess these risks, we have a strict 6-point failure mode checklist. We'll be moving through the HTS material shift, REBCO kinematics, quench detection, the thermal budgets, field ripple, and finally, structural fatigue. These are the mandatory engineering proofs required before any physical winding begins.
Starting with Item 1, the HTS material shift and redefining our operating bounds. Dropping from ambient temperatures down to a 20 to 30 Kelvin superconducting state completely rewrites the thermodynamic and structural rules of the entire system.
And here's the thing. Standard theoretical models are going to fail to predict yielding in this extreme environment. As technical reviewers, we need bounding parameters to be explicitly defined. Without pinning down the exact engineering realities, we are literally looking at structural shattering during the winding process or total thermal incineration during the very first quench.
Moving to Section 2, REBCO kinematics and yield constraints. We need to carefully evaluate the mechanical limits of the tape itself.
Before we even think about pushing current, just physically handling the REBCO tape during the winding of non-planar saddle coils is an immediate bottleneck. We have to ask, what are the absolute minimum easy access bend radii and the maximum allowable torsion angles for these commercial conductors? This single constraint dictates whether a modular array operating at 2 to 4 Tesla is even geometrically feasible.
To bound this realistically, we have to evaluate both 4mm and 12mm commercial tapes right inside that 20 to 30 Kelvin 2 to 4 Tesla envelope. It's absolutely crucial that we cross-reference exact substrate thicknesses, like 30 versus 50 microns, against those bend constraints. We're setting a hard yield limit here. If the critical current degrades by more than 5%, it's a failure. And on top of that, any post-cure thermal stress from our epoxy impregnation strategies has to be thoroughly validated.
All right, Section 3. Quench detection and propagation limits. Let's dig into the single highest thermal catastrophe risk in the active system.
There is a massive, terrifying disparity in thermodynamics here. With traditional low-temperature superconductors, the normal zone propagation velocity is fast. It's highly measurable. But with REBCO HTS sitting at 20 Kelvin, that velocity drops to a dangerously slow 0.05 to 0.1 meters per second. This means a quench doesn't just rapidly dissipate across the magnet, it localizes. It will literally incinerate localized hotspots before standard terminal sensors even register a voltage drop.
Because of that incredibly slow propagation, our quench discrimination requirements must be flawless. First, we have to mathematically define exact hotspot temperature limits alongside our dump resistor time constants. Second, we need to implement advanced co-wound sensors or differential voltage detection. And finally, we have to perfectly isolate true thermal runaway microvoltages from the ambient inductive noise generated by adjacent power electronics.
Next up, Section 4, cryostat architecture and our heat budget. We really need to manage these warm penetrations, bridging ambient room temperatures down to our 25 Kelvin cold mass.
Our baseline architecture relies on Gifford-McMahon conduction cooling. This is a closed-cycle cryocooler system that maintains that 20 to 30 Kelvin zone around a warm bore, without using any liquid cryogens. It's a great dry system, but operating it means every single sensor wire, electrode, and current lead crossing the vacuum jacket introduces a critical heat leak risk.
So we have to ruthlessly map out these established heat leak values for every ambient penetration. We need strictly defined thermal standoff lengths for instrumentation feeds, explicit G10 or FR4 material isolation profiles for high current leads, and exact multi-layer insulation configurations for the vacuum jacket crossings. If we fail to balance this thermal ledger, we will easily overwhelm the cryocooler capacity.
Moving on to Section 5, Modular Field Ripple Tolerance. Let's evaluate our electromagnetic fidelity.
Since we are working with discrete, modular saddle coils, spatial magnetic field deviations, or ripple, are simply inevitable. But how much is too much? We must explicitly quantify the maximum allowable magnitude deviation as well as the angular deviation from the continuous normal direction. Why? Because excessive ripple induces turbulent eddy currents in the working fluid. We need to calculate the exact mathematical threshold where parasitic drag completely negates our Lorentz force advantage.
Finally, Section 6, Structural Fatigue and Inductive Triggers. This brings us to Tier 2 constraints surrounding system interface and control logic.
We have to talk about the scaling factor because it's a massive structural threat. When we push this to 3.0 Tesla, our transverse Lorentz force scales up by a factor of 6 compared to our baseline ambient copper testing. A 6x jump is huge, and it severely threatens the physical integrity of the entire array.
Existing modular arrays absolutely must structurally isolate high-frequency mechanical shock waves from that highly brittle REBCO ceramic layer. If we don't have verified, engineered support strategies, like robust clamshell clamping and highly precise epoxy potting, these massive intermodule forces are going to instantly shatter the superconductor on the initial pulse.
Which brings us to a major unresolved failure mode. What happens if an H-bridge shorts and dumps a 100-amp transient into the system? That sudden change in current is going to induce a massive flux jump. So, how do modern HTS controllers mathematically separate that induced voltage spike from a genuine critical thermal quench? If the system triggers falsely, the whole thing crashes. If it ignores a real quench, we melt the engine. Defining this exact discrimination logic is the absolute final prerequisite we need to mathematically bound before any physical design of the module even begins. It's a complex puzzle, but absolutely crucial to get right.